Dear students, today we'll discuss about Maxwell's equations and we'll derive wave equation of electromagnetic wave. We get heat and light from the sun and these travel all the way in free space in the form of electromagnetic waves. First of all, we will take up Gauss' law of electrostatics. The law states that the total normal induction over any closed surface is equal to the total charge enclosed by that surface. We consider a closed surface. Actually, it is in 3 dimensions and it can be of any shape. There are electric charges inside and let the charge density be rho. We consider a small surface element ds. It is a vector quantity and the vector is directed towards the normal to the surface element. Because of the charges inside, there will be no electric field inside, but outside there will be electric field. Let the electric induction D be in this direction. And this D is equal to epsilon E. While epsilon is the permittivity and E is the electric field. The component of D along the normal to the surface element is D dot product with ds. And if we integrate over the entire surface, we get the total normal induction over the surface. We consider a small volume element dV inside. The charge contained in that elementary volume is rho dV. And if we integrate over the entire volume, then we get the total charge enclosed. And by Gauss' law, these two are equal. Now for converting this from the integral form to the differential form, we use divergence theorem. By divergence theorem, the surface integral can be written as a volume integral of divergence of d dv is equal to volume integral of rho dv, or volume integral of divergence of d minus rho dv is equal to 0. This gives divergence of d minus rho is equal to 0. This we can write as divergence of E is equal to rho by epsilon. Since no single magnetic pole can exist, so divergence of B, where B is the magnetic induction, is always 0. Now we will take up Faraday's law of electromagnetic induction. For this, let us consider a magnet. This is North Pole, this is South Pole, and have a metallic ring which can conduct electric current. Because of this magnet, there will be a magnetic field, and this magnetic field will be linked by this ring also. Now let us move this magnet towards the ring. So the magnetic field linked with the ring will be changing, and due to that an electromotive force will be induced into the ring, and this induced electromotive force will cause a current to flow in the ring, and the direction of the current will be such as to oppose the cause. So in this case the direction will be like this, that is the current will flow in this direction, so that if we look from this side, this will act as a south pole and south to south will repel. We consider a small elementary length dl This is again a vector. And the electromotive force linked with this elementary length is E dot dl. And if we integrate, and this is equal to minus del T of B dot ds, where ds is a small elementary area enclosed by this ring. Now this we integrate this over the entire length, and this we integrate over the entire surface. This is in integral form. We want to convert it to differential form. So we use the Stokes theorem. By Stokes theorem, this line integral can be converted into surface integral as surface integral of curl of E dot ds is equal to surface integral minus del T of B dot ds. Taking this to the left hand side, we get surface integral of curl of E plus del T of B dot ds is equal to 0. Or we can write as before, curl of E is equal to minus del T of B. This negatives I have already explained. Lastly, we'll take Ampere's circuital law. We consider a conductor carrying electric current. Let the current density be J. Because of this electric current, a magnetic field will be created around the ring like this. When the current density will be changing, the magnetic field created also will be changing. As before, let us consider a small elementary length dl on this virtual ring, and for that we get B dot dl is equal to mu into J dot ds. This is equal to dot ds, where ds is an elementary area enclosed by this virtual ring. Now what Maxwell did, he added one more term for induction current density. This is J is conduction current density, and he added one term for induction current density, and that value is mu del T dot ds. This we can write as mu J plus del T of D dot ds. Here J is the conduction current density and del T of D is the induction current density. Again we take the line integral, and this will be surface integral, and by Stokes theorem curl of B dot ds is equal to surface integral mu J plus del T of D dot ds. In this connection, we can say that the induction current is necessary because free space where there is no conduction current, there is no electric charge, it can sustain electromagnetic wave. So this we can write as curl of B is equal to mu J plus del del T of D. These are the four equations. In this connection, we can note that when there is a steady current, a steady magnetic field will be created. But when the current is changing, the magnetic field also will be changing. And these together form an electromagnetic wave. We can get changing electric current either by oscillation or by rotation of a charge. So the charge has to get an acceleration, then only electromagnetic wave is possible. A charge simply moving with a uniform velocity cannot create any electromagnetic wave. Now we take up this equation. Curl of E is equal to minus del del T of B. We again take the curl. Curl of E is equal to minus curl of del del T of B. This order, differentiation with respect to T and curl can be interchanged, and we can write as minus del del T of curl of B. Now for free space, epsilon is epsilon 0, mu is mu 0 for free space. There is no charge density, rho is 0, and there is no conduction current, that is J is also equal to 0. By vector identity we can write like this: gradient of divergence of E minus Laplacian of E, and that is equal to, we replace this with mu plus, then we get minus del del T of mu this is mu 0, and this is equal to minus mu 0 epsilon 0 this is double derivative with respect to T of E. Now this is 0, so we get Laplacian of E is equal to mu 0 epsilon 0 del to E by d2. Similarly, for magnetic field we can write like this: Laplacian of B is equal to mu 0 epsilon 0 here in this case double derivative of H with respect to T. For a plane wave, that is plane electromagnetic wave, there will be component of electric field in one direction, and perpendicular to that there will be component of magnetic field, and both are changing with respect to time, and that is why an electromagnetic wave is created and it travels in a transverse direction. So a plane electromagnetic wave can be represented as This will keep. This is x-axis, origin, y-axis, and this is z. Let the electric field be changing along the x-axis. So this is electric field. And the magnetic field will be changing along the y-axis on the yz plane. So let it be E and it be H. In that case, only X component of electric field and Y component of magnetic field will be applicable. So this Laplacian can be written as double derivative of E with respect to X, and that is equal to mu 0 epsilon 0 double derivative of E with respect to T. Similarly, for the magnetic component, it can be written as double derivative of H with respect to Y is equal to mu 0 epsilon 0 double derivative of H with respect to T. These are familiar wave equations, where the velocity is, that is velocity Vc is equal to 1 by mu 0 epsilon 0. If we put the value of mu 0 and epsilon 0, that is mu 0 is equal to 4 pi into 10 to the power minus 7 Henry per meter, and epsilon 0 is 1 by 4 pi into 10 to the power 9 into 9 farad per meter. And if we put this value, we get 3 into 10 to the power 8 meter per second. This is the speed of light in free space. Thank you.